Yeah, right. There you go. It's starting.
So do you see the screen well? Is it?
Not yet, Faranak. There's a slight glitch, I think, in your connection at the moment. You may have to log out and back in, I think.
Oh, it doesn't show. It doesn't.
Now it does.
It doesn't show. Oh, no, it does. Okay.
Yeah, it's good now. Yeah.
Oh, okay. So the topic of the talk is interior point methods in linear and convex programming. I'm going to start with an example of a linear programming problem, some introductory topics to optimization, then the primal dual interior point method for solving linear programming problems. And then interior point methods in convex programming. Then I'll move to analytic center cutting plane method, and finally nonlinear programming with constraints given by a separation oracle. This is actually one of the problems that I worked on for my PhD thesis. And finally, the conclusion. So let's start with an example of a linear programming problem. Consider maximizing an objective function, z 3x1 plus 5x2, subject to these constraints, which we call the feasible region. And I have drawn this feasible region here. X1 and X2 are positive.
I'm sorry.
X2,
yes? Sorry. May I ask you to maximize that screen?
Okay. Is it better this way?
Yes, please. Thank you.
Okay, it's better. Okay. So we maximize this objective function 3x1 plus 5x2 subject to these constraints, which is our feasible region. I have drawn it here. 3x1 plus 2x2 less than 18 is this line, and this is our feasible region. When we apply simplex method to solve this problem, it starts from this corner point or extreme point and moves to the next extreme point on which the objective function increases to 30, and then finally to the third one, which is 36. So if you use a tableau for the simplex, it starts from point 1 to 2 to point 3. And if we use a interior point method, on the other hand, it starts from a point in the interior of the feasible region and moves towards the optimal solution, following a path which we call a central path. Any questions about this?
It's good.
Okay. Everything's good? Okay. So
I have one question.
go to the...
Faranak?
Yes, yes.
I have one
Yes.
question. What happens
Yes.
if the polygon is not convex?
Then these are all convex programming. So we only look. So you could, if the inequalities are, you can convert. If you have greater or equal, you can convert to less than equal, but it's only for convex programming.
Okay.
So the building blocks of interior point methods are three things. One is Newton's method for finding a zero of a vector function, or for unconstrained minimization. If you have an unconstrained minimization, like minimizing g of x, then we look at the gradient of that, which becomes our vector function, or like a transformation. So when we want to find a zero of that, we use Newton's method, which is an iterative method and uses the Jacobian of this transformation. And it's usually written in this format. Jacobian of sk dx is the Newton step, and minus the value of the transformation at the current iterate. The second thing that's used in optimization problem with equality constraints, that is to minimize a function subject to m equality constraints, is method of Lagrange from 1788, that a Lagrangian is formed. We include the objective function and we include a linear combination of the equality constraints into the Lagrangian. So the constraint optimization is converted to a unconstrained one. And Newton's method can be used to find a minimum of that. The third thing that is used in interior point methods is the method of Piaco and McCormick from 1968. It's called the barrier method, and that takes care of the inequality constraint. So if we have to minimize an objective function subject to, I only chose the simple inequality constraint of all the variables being non-negative, then how are these inequality constraints taken care of? They are formed into something called a barrier function. So we have the objective function, and we take this ln of xj. These are the components of the vector x from j equal to 1 to n. And there's a parameter mu. We parameterize this barrier function with mu. And this ln makes sure that all the variables stay strictly positive. And as when mu is very large, the weight of this part is high. So the minimum of the barrier is moved towards the minimum of this part of the barrier function. But as mu gets smaller and smaller, this part becomes less significant, and the minimum moves towards the minimum of f of x. And that's the idea of a barrier method. So this constraint optimization can be replaced by a family of unconstrained minimization problem. And for each mu, there is a minimum for this. We call it x of mu. As mu moves to 0, x of mu, which is a solution of that, moves to the optimal solution of the original problem. And this path formed by x of mu is known as the central path. And there's some remarks I wanted to make because we talk about polynomial-time algorithm. Roughly, like informally, what it means is that if m is the number of constraints in our feasible region, n is the dimension of the problem, and epsilon is the accuracy of the solution, and h of m, n, and epsilon is an upper bound on the number of arithmetic operations required to find an epsilon solution, then by polynomial time algorithm, we mean that this upper bound is a polynomial in m, n, and ln of 1 over epsilon. If this upper bound is a polynomial in m, n, and 1 over epsilon as opposed to ln of 1 over epsilon, then it's called pseudo-polynomial. Now, there are many variants of interior point methods for linear programming. Before Karmakar's algorithm, even Hoshian had one, but it was very slow in practice, so it didn't get much attention. Karmakar's algorithm was more efficient in practice, so he started this, but many other variants soon were derived. The primal path following, dual path following, primal dual, but there are so many of them. I have selected only one of them to present here, and that is called the primal dual path following method, basically. And that's the one that's theoretically, it's been the most elegant one, and computationally the most successful one. So I will only talk about that one. The primal dual interior point feasible method for LP. This method, the underlying theory of that was developed by Megiddo in 1986, and the convergence of that was established by Kojima, Mizuno, and Yoshi in 1988. So going into a linear programming problem, it's formulated in a minimization form, minimizing C transpose X. This is known as our objective function. AX equal to B our equality constraint. X, all the variables are non-negative. These are the inequality constraints. We call this the primal feasible region. Every linear programming problem has a dual problem. And the B and C that you see here also used here. The A is the same, is A transpose here. So it's the same parameters, but it's formulated as a maximization problem. The S, which is C minus A transpose, is the vector of a slack variables. And what is the relation between primal and dual? If we have an optimal solution for the minimal, and 1 for the dual, the value of the optimal function, the optimal value of the objective functions would be equal. In other words, if x star is optimal solution for this, y star is optimal solution for this, then C transpose x star would be equal to B transpose y star. In other words, we say the duality gap is 0. Otherwise, if we have a feasible point for here and one for here, B transpose x is always bigger than B transpose y. There is a gap between them. And as the iterates move towards the optimal solution, the gap becomes 0. So it's important to consider both of them in this method because it accelerates the convergence. This is known as the dual feasible set. So as I was mentioned, we can handle the equations by Lagrangian and the inequalities using the barrier method. And we can have one, we still call the Lagrangian for LP and one for LD, the dual problem. Here they are listed. So this is the Lagrangian associated with the primal problem. The inequality constraints are put in the barrier, and the equality constraints are given here using the method of Lagrange in matrix vector form. Same thing for the dual problem. Now, if you write a necessary and sufficient condition for this, because these are convex functions, the optimality conditions are both necessary and sufficient, and it can be shown that if we put the gradients equal to 0, there is some algebraic manipulation involved, there's some duplication, but if you write the optimality conditions, we get this system, which is a nonlinear system of equations. The first one is actually part of the primal feasibility. It has to be on AX equal to B. The second one is the dual feasibility here. And this one is known as approximation to complementary slack. So writing the optimality conditions leads to this system, which can be now solved using Newton's method. We bring everything to one side. We can write this in matrix form. So we form this capital X and capital S, which are diagonal matrices with these variables on the diagonal. And E is a vector of all ones. So this is written as a system for which we want to find a 0. And we can apply the Newton's method. A good starting point is required. And again, there are different papers that can be written to see how to have a good starting point for this, but it's not the scope of this talk. But we have a starting point where both x0 and 0 are strictly positive. And this is the Newton system. This is the Newton step. This is the Jacobian of this transformation. And this is a negative of the value of this at the starting point, x0 as 0. So it's b minus ax0 is represented by dp. And if you put y0 as 0 here, the difference is dd. And this is our system. The way this system is solved is this is a partition matrix. Again, there's some algebraic manipulation. First, they find dy from this system. And LU factorization is used here to solve it. It's some form of it called, the U is L transpose, is known as Cholesky factorization. And there is a lot of computational effort required for this part. And once dy is found, then ds and dx are calculated after that. So the next iterate, once we have calculated the Newton step, the next iterate is calculated taking steps in dx, dy, and ds. And they are chosen such that x1 and s1 remain positive. Again, there are many papers written on how to choose these efficiently. So the algorithm converge faster and faster. So this is one iteration of the algorithm. We start from a point, we apply one Newton step, and we find the next iterate. The next thing is to reduce the barrier parameter mu, because if you can try to minimize this or maximize this, the primal barrier, the Lagrangian or the dual Lagrangian. So we need to reduce the barrier parameter mu. And it has to be reduced wisely so that the algorithm converges in polynomial time. And one way to choose that is to reduce it like this, because this is based on the duality gap between the primal and dual. And it's been successful. It leads to polynomial time convergence. I'm going to show you how it works. So it basically is like this. This is only the primal feasible region, and something similar also works for the dual feasible region because it's optimizing both. So when mu is large, we start the objective function becomes less important, and it moves towards the central point in the feasible region, which is called analytic center of the feasible region. So the algorithm starts close to that, and this red path is the value of all the x of mu, the exact minimizers of those barrier functions. But the algorithm tries to follow this path closely, so depending on whether it wants to follow it very closely or not so closely, we have the longest step, short step, and different ways. But in general, these yellow points are the ones that are generated by the algorithm that follow this red path towards the optimal solution, as I mentioned. And going back. So that's basically the general idea for interior point methods for linear programming. Now, because interior point methods were originated from solving nonlinear programming problems, they suit convex programming problems very well. So what is a convex programming problem? It's a generalization of a linear programming problem. Therefore, the functions have certain properties. The objective and the constraints are all convex. I have only included inequality ones here. What do we mean by a convex set? If 2 points are in the set, the line segment joining them should be also included in the set. And the functions are convex in a sense that they have to have this property. If we take a convex combination of 2 points and evaluate the function as that, it should be less than or equal to convex combination of the images. In R, if y is a function from R to R, y equal to x2, y equal to minus ln of x, y equal to ex, they are all convex functions. In Rn, if we look at the functionals, linear and affine functions are convex. Convex quadratic functions, in a sense that a quadratic function that where p is positive semi-definite is also convex. The thing that we had in the barrier function, minus sigma ln of xj's, that would keep the xj's strictly positive, is also convex. And if you have a concave function, minus f is convex. If we have positive multiple of a convex function, it will be convex. Sum of convex functions is convex, so it has certain properties. There are, again, many different kinds of interior methods for convex programming, similar to the ones that existed for linear programming. But I only talk about one of them because more or less they're based on the same idea. That's the primal barrier method. So we have a barrier function associated with our convex programming problem. We take the objective function again and put this in the ln to make sure they are all strictly negative. So it's ln of minus fi of x. And this is the barrier parameter. The original problem is replaced by a sequence of unconstrained optimization problems parameterized by this barrier mu, similar to what is done for linear programming. Then for each mu, there is a minimizer for this barrier function. We call it x of mu. And again, when mu is large, this is less significant. This is weighted more. So it starts with the analytic center of our feasible region. I'll talk more about analytic center a bit later. But as mu moves towards 0, the objective function becomes more and more important. So the minimum moves towards the minimum of the barrier function. This x of mu, where mu is positive, is called the central path. And as mu goes to 0, x of mu approaches x star. So it's important to have certain properties and choose a reduction of mu again wisely to make sure the algorithm converges in polynomial time. And this minimization again is done by, for each mu is done using Newton's method. Now, there was an important contribution by two Russian mathematicians, Nesterov and Nemirovsky, in 1989, that extended the polynomial time complexity results to convex optimization problem. Their important contribution was this definition of what they call self-concordant functions. Self-concordance is very important to prove the algorithm, the interior point algorithm that was mentioned, would converge in polynomial time. So what is the self-concordancy? If we have a convex function, basically these are functionals. A convex function, that then we call it alpha self-concordant if it's 3 times continuously differentiable, and this is the property. The third differential of the function at x in the direction h is less than or equal to 2 alpha. This is its Hessian, h transpose Hessian of f times h to the power 3/2. What does that mean? In the motivation behind this is that this means that Hessian of this functional is Lipschitz continuous. Basically, it's Lipschitz continuity of the Hessian that's important for this a key to make the algorithm polynomial. Of course, together with a wise reduction of mu and taking the Newton steps efficiently. For example, the logarithmic barrier function that is here, if we have linear constraints or convex quadratic constraints, the logarithmic barriers would be self-concordant with alpha equal to 1. They are 1 self-concordant. So that was the important contribution, the self-concordancy property of the barrier function. The next topic is, again, another class of convex programming problem, is known as large-scale optimization, which they use a method called cutting plane method. Cutting plane is just a separating hyperplane. When in large-scale optimization, there are too many constraints, or so the feasible regions are usually auto-approximated because it doesn't make sense to have too many constraints in here. It's just there's too many, so they only add them as they need them. So they call it column generation or cutting plane, which the constraints are auto-approximating the feasible region. So using interior point methods in cutting plane methods was originated by Jean-Louis Goffin, my PhD supervisor, and his co-worker Vial from Belgium. They're both Belgian, in 1993. And he called this mixed method analytics. They call this method analytic center cutting plane method. So the cutting planes, instead of being added at the exterior of the set, that the polytope that contains the feasible region, they're added at central points, which they call, again, the central part of the feasible region, which is called analytic center. And later they established the complexity bound with the help of Liu and Ye in 1996. So what is analytic center of a polytope? I'll show you first. If you have a convex polytope, as you see here, the analytic center is a point that has maximum distance from all the faces of that cos-convex polytope. And mathematically, if you consider a polytope in the dual form, it looks like a dual feasible region. And these are the vector of S, because C minus A transpose, the vector of slack variables. Basically, is the distance to the faces of that polytope. Mathematically, it's like minimizing this function minus sum of j equal to 1 to n ln of sj. This is known as the dual potential. It has some similarity with the barrier, but here only we want to find one point in the interior of feasible region that has maximum distance from all the faces defining the polytope. So this is the same as maximizing product of all these SJs. And this concept was studied and introduced first by Sonnevand in 1986. And it's been used a lot in large-scale optimization. How do we find that? Again, is using necessary and sufficient optimality conditions lead to a system similar to what we saw before. But in practice, only approximate analytic centers are being used. So something that would satisfy this, the equality conditions, but the last one is only approximated. So again, Newton method will be applied to find the analytic center. So I use some of this method in solving this problem. So the next problem depends on these analytic center cutting plane method. So this is the problem I worked on. For one of the problems I worked on for my PhD was having a convex problem. Our objective function is convex and C3 is smooth, but the feasible region is so large, or it could have pseudo-convex constraints even, which are weaker than convex, but they still can be solved using this method. That's why we call it nonlinear programming. They could be convex, they could have linear constraints. Many of those can be approximated by linear. We look at the linear approximation of a lot of those functions defining our feasible region. So there are certain assumptions we have. We assume the feasible region is a closed convex set. We assume it's contained in a unit cube. We use unit cube to make the complexity analysis simpler, but it can be scaled, this unit cube. And we assume our feasible region is either empty or is not too small, in a way that we can put a full dimensional ball of radius less than 1/2 in it. And here's a more explicit definition of what do we mean by gamma is implicitly defined by a separation oracle. So we have a point, we start with this unit cube. We have a point in the unit cube and we check whether it's feasible or not. We call the checking of that being tested by the oracle. If it's feasible, the algorithm says yes, the oracle answers yes. Sorry. If it's not feasible, then it answers no, but it generates a cut, which is basically a separating hyperplane with the property that our feasible region is included in the half space that's defined by that hyperplane. An example of our feasible region is this. We have a bunch of these constraints, but there could be even infinitely many of them. These functions could be convex, linear, they could be even pseudo-convex. They don't even have to be differentiable. So when a point is given to the oracle checks to see which one of these constraints is violated. If it's a linear constraint that's violated, it simply returns that cut in a way that the feasible region is included in the half space. If it's not, if it's a nonlinear constraint that's violated, it will generate, it will approximate it with a linear function. It looks at linear approximation of that and generates a hyperplane from that. So it could be using, if it's differentiable, a gradient of that, like a tangent plane. If it's non-differentiable, it uses a subgradient to generate that hyperplane. So it's based, so constraints of this feasible region are added as they're needed, as we need it, as we need them. And so that's what it means, the feasible region being implicitly defined by an oracle. In other words, gamma is always author approximated. And there are other assumptions we make for this problem. One of them, because we are considering the nonlinearity of the objective function, we assume that this function is self-concordant. This is a barrier function to make sure the iterates stay inside the unit Q. This is corresponding to the level curve of the objective function. So together we have a very similar to the log barrier function, but here we call it potential because instead of mu, we have this z, is parameterized by z, which is the upper bound on the objective function. Again, so the problem becomes like an unconstrained minimization problem, but gamma is implicit. So we, instead of gamma first, we start with the unit Q. And then we add the constraint as they are needed to this barrier. So self-concordancy is very important here because we're considering the nonlinearity of the objective function. And our goal is to find an approximate solution, an epsilon solution. That's a solution that if we evaluate the objective function at y epsilon, and if f star is the optimal value of our problem, it's only within epsilon of that. I talked about analytic center. We also need to look at analytic center of set of localization. What do I mean by set of localization? It's a set like this. These are author approximating the feasible region, whereas this is the level curve of our objective function. So each time we need to look at the analytic center of this to add the new cuts. So very similar to the analytic center of a polytope. The only difference is that one of the constraints we have is nonlinear this time. And the unique solution of that is known as analytic center. Here it is. So this is the set of localization. We had, this is a polytope that approximates our feasible region. And here's the level curve of our objective function. We have a set called set of localization, and analytic center of this set of localization is a point that has maximum distance from all these constraints, including the level curve of the objective function. So how does this algorithm work? How does this find a solution? First, I'll show you the graph. So graphically, this is the unit box, which I'll call it omega 0, that contains the feasible region. The feasible region gamma is implicitly defined and is shown by this ellipse here. We start by, the algorithm has two phases. At first phase, in the first phase, we have to find an interior, a feasible point. So we start the center of the unit. Analytic center is exactly the same as center of that unit Q. We check by the oracle if this is feasible. If it's not feasible, like you see in this case, we add a separating hyperplane, and we know that the feasible region is on this side. After that, we look at this author approximation of the feasible region. We find this approximate analytic center. We notice, check the oracle if it's feasible or not. It's not. So we add another cutting plane, and we find the new analytic center, and this one is feasible. So once we find a feasible point, then we add the level curve of our objective function. So we're trying to localize the optimal solution this way. So we have now a set that has a nonlinear constraint in it, and the rest of them are linear. Then once we find a feasible point and we add that, we find the analytic center. We have our first set of localization. We find the analytic center of this set of localization. If it's feasible, then we check for optimality. If it's not, which is what I've drawn here, then we add a feasibility cut. And then the next step, again, we find the analytic center. That one becomes feasible. And then once we find a feasible point, we check if that's optimal or not. How do we check? We check if it's the difference between the value of the function at that point, and the upper bound on our objective function is very small or not. If that's the case, we stop. So this is called the cutting plane algorithm with a nonlinear objective function. Now here it's the same thing that was I showed you through a diagram, but this is the algorithm. It has two phases. At phase one, we use analytic center cutting plane method and separation oracle to find out whether the set feasible is empty, or if it's not empty, we find a feasible point, original feasible point. And once we find that, we add the nonlinear cut to form the set of localization. In the second phase, we find an approximate analytic center of this set of localization, check for feasibility, and until we find a feasible point, and we check for optimality. If it's not optimal, we lower the upper bound on the objective function. And this is repeated until we find an optimal solution. And we have shown that this algorithm finds an epsilon solution in pseudo-polynomial time. The pseudo-polynomial time is due to these cutting planes. When they are being added, they make the algorithm only pseudo-polynomial. So in conclusion, it's not generally accepted that interior point methods for linear programming are competitive with simplex method and often faster for large-sized problems when there are more than 10,000 variables and constraints. Knowledge of both methods for solving linear programming is important. In fact, when optimization courses are taught at universities now, they have all included at least one linear interior point method for solving linear programming together with simplex. So basically, they complement each other. It's the knowledge of both is important. And if the software that is developed for solving linear programming now has both simplex and some interior point algorithms together. And because they initiated from solving nonlinear programming problems, they were easily extended to from linear to nonlinear. But simplex method is only for linear programming problem. It doesn't have any counterpart for nonlinear programming. And one area of nonlinear programming in which interior point methods have been very successful, both in theory and in practice, has been an area of positive semi-definite programming. They usually show it by like SDP, which is an extension of linear programming problems where the variables are replaced by symmetric matrices. And there is still, to this day, it's a very popular field in optimization, and the use of interior point methods in semi-definite programming was originated by Alizadeh in 1991. And because many convex optimization problems, linear programming, convex, quadratically constrained quadratic program, can be cast as semi-definite programming, as many other, also several other nonlinear programming problems can also be cast as that. They have many applications in control theory and combinatorial optimization. So I'll stop the talk here. Any questions?
No.
Okay.
I have a comment, if I may. I mean, I took a certain number of linear and even nonlinear programming courses in university as an undergraduate. But of course, this is bringing me back to the early 1980s. So I'm enormously impressed by the incredible amount of change and progress in that time. I mean, this looks like a completely different subject now, almost. Although I note that they use similar language and some of the ideas seem to harken back to things that I learned, but this is really very, very interesting.
Yeah, that's right. actually Karmakar in 1984, he started the revolution. Because like the simplex, and then when they became interested in the complexity of, like until early 1980s, it was just simplex method. You know, you just had to talk about simplex method. But since then, when they got interested in complexity of the algorithms, Karmakar's algorithm started a revolution, because thousands of papers have been written in the field since then.
Right.
And it's just like, yeah, exactly. It's like it's a completely new field now. Now, no one, as I said, anyone who teaches linear optimization course, linear programming, they have to talk about some form of nonlinear programming problems as well.
Right. I see. Oh, by the way, I guess I'll stop recording. Is that would that be appropriate now? I'll stop the recording.
Yes.
Okay. Here we go.